Okay, anybody have any homework questions? Okay, yeah. Anyone? Yes. Okay, so this is particle kinetics. Number 26. Um, so the left incline, this is 20 degrees. And this one is 30 degrees. And you have a pulley in between and a cart on each incline. This one has a mass of 10 kilograms. This one is 12. And a pulley connects them going over, or a cable connects them going over that pulley. And we want to figure out the accelerations and the force vectors applied by the cable. The only thing causing them to accelerate is the weight. And on both of these, since on both sides this is rolling or sliding, we're going to use coordinate systems with the y-axis pointing out and the x-axis along the surface. Which sort of brings up the question, so is it okay that we're going to do a single problem with two different coordinate systems? And the answer is, as long as your variables are related to each other, as long as the variables make sense with each other, all we're going to do is come up with some equations that are true over here, and we can use whatever coordinate system we want to come up with equations that are true. And we're going to come up with equations that are true over here. It's going to give us a system of facts that are true, and then we'll solve those as a system. So what you have to be careful about is if we came up with an acceleration vector in this coordinate system, or a force vector in this coordinate system, and then used it over here, that, the components here do not match the components here, okay? So we just have to make sure that whatever variables we use make sense in both of those two cases. Well, what that means in this case is if you move this one an inch in the positive x direction, in its positive x direction, where does this one go? It goes an inch in its own positive x direction, okay? And so we can treat this acceleration vector as a0, and then say if this one has an acceleration of a0, this one also has to have an acceleration of a0 in its own coordinate system. So actually, mathematically, that's pretty easy to do, okay? So let's go through this. We're going to just do a free body diagram and Newton's second law for each one of these. So I'll start with a free body diagram of the 12. There's a weight of, what's 12 times 9.81? Is that 1177? Or 117.772? Okay, and then there's a normal force. I'll call that N12. And then there's a cable force. Both of these two force vectors for the cable tension and the normal force are easy to represent in our rotated coordinate system. We just have to figure out the components of the weight force. So here's our coordinate system. Here's the weight force. The angle that the weight force makes with the negative y-axis in the rotated coordinate system is the same as the angle between the horizontal and the ramp. And so that means this angle is 30 degrees. And so the angle from the positive x-axis is, you go all the way to 270 and then 30 degrees farther. So 300 degrees. And so that weight force is 117.2 times cosine and sine of 300. Can someone tell me what those are? 58.86. Okay. And what's times sine of 300? I'll do the sine, it's negative. What? Negative 101.9, what? Hi. Okay, so now we can go to Newton's second law. We have 58.86 for x, negative 101.95 for y. Then we have the normal force in the positive y direction, 0 and 12. And then the cable force in the negative x direction. And that's all equal to the mass times the acceleration that we know is parallel to the x-axis of our coordinate system. So I'll write that as a0. If we wanted the normal force, we could use the y equation. But the x equation tells us, I'll write it as 12a plus t is equal to 58.86. And we can't solve that yet. It's two variables with one equation. So now we'll go to the other body. There's a weight force of 10 times 9.81, so 98.1. There, I moved it to the, yeah. Okay, and then we have the normal force, N10. And then the cable force, this time it's going this way, but it has a magnitude T. So figure out the components of the weight force. This angle is 20 degrees. So from the positive x-axis, you can think of it as coming 20 degrees, you're coming up 20 degrees short of 270, so theta is 250. And so the vector components are 98.1 times cosine and sine of 250. And what do you get for those? Negative what? Okay. 92.18. Okay, so now Newton's second law says negative 33.55, negative 92.18, plus 0 and 10, plus positive t0 is equal to the mass, 10, times the acceleration vector of this cart. So now is where you have to be careful about making sure your accelerations match up. And you can do it two ways. If you see the relationship right off the bat, you can just put it in using the same variable. In this case, it's just going to be, like we said before, if the other one has a positive x acceleration, this one has a positive x acceleration of the same magnitude in its coordinate system. But if you don't see that, you could do one as like A12, 0, do the other one as A10, 0, and then come back when you see at the end that you have too many variables and not enough equations, and come up with a relationship between those two variables. But I put it in here so we don't have to mess with that. The x equation here says 10a minus t is equal to negative 33.55. And now we have this system of equations, the two boxed equations. If I add those both, those two equations, the way they are right now, the t's cancel each other. But you're just solving this system of equations however you want to do it. And you get 22a is equal to 58.86 minus 33.55. What's that? 25 point what? 11? 31. What was it? 58.86. And so then you can find a, what's 25.31 divided by 22? 1.15 meters per second squared. Okay, so what does that say about the acceleration vectors? You just plug that variable back into either one of these to find the acceleration that you're asking for. And we get that both of them are accelerating in their positive x directions with a magnitude of 1.15. And then if you wanted to calculate the force that the cable's applying to either of these two carts, just substitute back in to get the t value, and then put the t value in one of these two force vectors. So anytime you're isolating an object that's rolling or sliding, you want to choose a coordinate system with the y-axis pointing out of the incline. Including, there's one in the homework where the thing's sliding up a wall or down a wall or something. Even if you're sliding something across the ceiling, it seems a little odd, but just choose, if you're sliding something across the ceiling or rolling something across the ceiling, the y-axis should be straight down, the x-axis should be straight along, and then a lot of things come out just the way you're used to them coming out. The normal force is 0 and, blah, blah, blah. Any other questions about that one? Any other homework questions? 29? Ooh, that looks hard. Okay, so you got this wall with a pulley attached to it. And that's attached to a block on an incline. And the other is attached to a mass M3. And the block is attached to a cart by a spring. The cart has a mass M2. The angle between them, the angle between the horizontal and the ramp is theta. The sliding block has a mass M1. The coefficient of kinetic friction here is mu. Since we're talking about kinetic friction, we have to know the direction that these are moving at this instant, direction of the velocity. And I guess it changes for A and B. Okay, so for part A, we want to give an expression for the acceleration vector of mass 3 assuming that M3 has a downward velocity, I guess I'll say. It says moving down, but that's equivalent. And we're going to do the same thing, I think, with a upward velocity. Most of the problems that we do give no mention of what direction things are moving. Why does this one? What is it about this one? There's only one kind of kinetics problem where we care about the direction of the velocity, and that's when we have kinetic friction. And the reason is, whatever direction this thing's sliding, the kinetic friction is mu times the normal force in the opposite direction. Okay, so for parts A and B, we're going to have a friction force that has opposite directions, and so it's going to change the acceleration. And after this is done, let's think about whether it's speeding up or slowing down too. Okay. One other thing about this, the problems that we're doing with springs right now, I haven't talked anything about vibrations, oscillations yet. So you might think this can be sort of a confusing thing. Like, okay, what if you were holding those at rest and then you let this thing go? You have this intuition that that spring would, there'd be some bouncing going on, okay? But the spring problems that we're doing are all assuming that that spring in this environment is staying at a constant length, okay? So we're not dealing with any accordioning. What? Right. It's like, well, it can be like a cable in tension, like it will be in this case, or it can be like a pushing force if it's compressed. That won't happen here. But the thing is, it's always going to have some deviation from its resting length. Okay. So we are going to have to deal with the fact that the length has changed. It's just that whatever it's changed to, we're treating it as a constant in this problem. Okay. Um, so for part A, uh, M3 is moving down. That means that the ramp and the block are sliding up the ramp. Uh, there are a few ways to do this. I'm going to try first isolating the block and the cart as a single thing. Okay. I think this will work. Okay, so there's those, and then there's the spring. Here's the cart. Okay. And for these two, when we come up with equations, we're going to use the rolling and sliding coordinate system strategy. When we get to this one, we'll just use our regular coordinate system because there's no reason to mess with it. All right, so if this is our system, what are the loads acting? There's a weight force, and that's equal to the combined mass times 9.81, so that's M1 plus M2 quantity times G. And then there's a pushing force there from the ground. I'll call that N1. And there's a pushing force here from the ground. I'll call that N2. And then there's a friction force on the block. We're assuming that these are moving up the ramp. And so the friction force has to be this way. And what's the magnitude of that friction force? What? Yes, exactly. It's the coefficient of friction times only the normal force pushing the block to the surface. The normal force pushing the cart to the surface doesn't create any friction. So this is mu N1. And then there's one more force, the cable force going this way. Well, yeah, I mean, it's not really, don't think of it in terms of like the forces that are like trying to be applied. It just has to do with what direction it's moving at this instant. Those things are sliding and rolling up the ramp. And so the kinetic friction is down the ramp. Exactly. Okay, and then let's figure out the direction of that weight force, the components of that weight force. Um, this has a magnitude of M1 plus M2 times G. this angle, what's that angle there? That's theta, yep. And so our total here, you can think of that as, yeah, 270 plus, oh, yeah, let's not write it like that. So actually, we're not going to want to do that in this case anyways, because, I mean, you could do it that way and use cosine and sine of 270 plus theta. Um, but let's instead just use SOHCAHTOA on this one and come up with those components. Okay, so think of this as a right triangle. And we're just going to use SOHCAHTOA to figure out those two legs of the triangle. So this one is going to be the quantity M1 plus M2 times G times the sine of theta, because that's the opposite leg. And this one's going to be the quantity M1 plus M2 times G times the cosine of theta, because that's the adjacent leg. And then we're in the fourth quadrant, so we're going to have a positive x and a negative y. And so I'm going to write this weight force vector as the M1 plus M2 times G times sine theta for the x component, and negative M1 plus M2 times G times cosine theta for the y component. Okay, so the nice thing about using the full angle from the positive x-axis all the way around your vector is it's always cosine for the x component, sine for the y component, and the plus minus signs work themselves out. Okay, if you use SOHCAHTOA, you have to think about what leg is what, and you have to apply the plus minus signs on your own. Okay, but it makes a little simpler looking expression in the case where you're doing it symbolically like this. So that's why we did it that way here, you know, without having the 270 plus thing added in. Okay, so Newton's second law now says quantity M1 plus M2 times G times sine theta. And then the y component is negative quantity M1 plus M2 times G times cosine theta. Plus 0 and 1 plus negative UN1 0 plus negative T0 plus 0 and 2 is equal to the mass of the system times the acceleration vector. Question? Oh yeah, I'm sorry. Yep. And then the acceleration, like all rolling and sliding problems, is only going to be in the x direction. So I'll write that as A0. Um, so what do we have? We have these two equations. Uh, so the first one says quantity m1 plus m2 g sine theta plus mu n minus t is equal to the quantity m1 plus m2 times a. The second equation says negative quantity m1 plus m2 times g cosine theta plus n1. This mu n should be mu n1. Then back to equation 2. N1 plus n2 is equal to 0. How many variables do we have here? We have to figure out which of these are constants and which of these are variables. The constants, the thing that things we're solving in terms of, are m1, m2, g, mu. Yep. And then the variables are everything else. Oh, and theta, I'm sorry, is also a constant. The variables are n1, n2, t, a. So we have two equations, four variables. And so we have to keep isolating things, keep coming up with laws. Yep. Those are not provided, I mean, I guess the easiest answer is just the difference between the stuff that's provided in the problem and the stuff that that isn't. Okay, so now let's do a free body diagram of the hanging mass. So here we have T and M3G. And here it's not rolling or sliding, so we're using the normal coordinate system. So Newton's second law says 0T plus 0 negative M3G. Is equal to the mass of 3 times the acceleration. So now we have to think about how this would accelerate compared to the acceleration of the other stuff. If the other stuff is accelerating in its positive x direction down the ramp, how is the hanging mass accelerating? Positive y, yep. So I'm just going to write this as m3 times 0 a, positive a. The x equation doesn't give us anything. The y equation does. So I'll write that as t minus m3a is equal to m3g. And that's our third equation. We didn't add any new variables, but we still have one more variable than we have equations. So now we have 4 variables, 3 equations. I guess I'm sort of used to getting all the variables on one side and the constants and stuff on the other side in case you have to solve it by reduced row echelon form with a matrix. But it doesn't matter. I mean, it doesn't really change anything for us. Any other questions? Okay, 4 variables, 3 equations. So now we're going to isolate the individual bodies. Um, so let's do a free body diagram of mass 1. So there's a weight force of m1g. There's a normal force of n1. There's a friction force down the ramp of mu n1. There's a force applied by the spring, Fs. We haven't seen that before. What? I just called it force of the spring. That's the force the spring's applying to this box. And then we have this force T that we have seen before. Weight force is, the angle is the same as it was before. So we have m1g times sine theta for the x component, negative m1g cosine theta for the y component. And now we can go to Newton's second law. And we have m1g sine theta, negative m1g cosine theta, plus negative t0, plus fs0, plus 0n1, plus mu n1, 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, okay. And then that's equal to the mass, m1, times the acceleration, which we've already said is a0. If we use the x equation, we get a new equation and a new variable, okay? But notice that if we just take the y equation, we don't get any new variables, and we just solve for one of the variables we've already come up with. So the y equation says, I'll write it as n1 is equal to m1g cosine theta. We can think of that as our equation 4, and now we have 4 equations for 4 variables. Okay, so I'm first going to substitute in for n1. Let's see, where do we have that n1? Well, the only reason we used the y equation here at all was because it had n1 in it, because we need it in equation 1. So this one doesn't help us anymore. So I'm going to plug equation 4 into equation 1. And we get this new equation 1 that says the quantity m1 plus m2 times g times sine of theta plus mu times our new expression for n1 minus t is equal to the quantity m1 plus m2 times a. Okay, that one looks pretty good. What do we have now? In this one, we have two variables, t and a, and we can just use that with our y equation, our equation 3. That says t minus m3g minus m3a is equal to m3g. And now this is our whole system. That's two equations for two variables. We're trying to solve for a. So we can say t, the third equation says t is equal to m3 times separate m3a plus m3g. And then I'll plug that into equation 1. So we have the quantity m1 plus m2 times g sine theta plus mu times m1 times g cosine theta minus t, and I'm going to substitute in this expression, minus m3a minus m3g is equal to the quantity m1 plus m2 times a. Move the m3a over to the other side. And this is all equal to the quantity m1 plus m2 plus m3 times a. And now a is equal to all the stuff on the left side divided by the sum of the masses. Okay. So if you think of it as, if you think of this as a set of steps you have to follow to do this problem, then this problem looks really, really scary, right? But if you think of it as all you're trying to do is isolate objects and write out Newton's second law until you have a system with the same number of equations as you have variables, you know, and it's not really a set of rules I followed. I was just isolating bodies until I found a system I could solve. Then it's really not that bad. There's a lot of algebra and stuff, but conceptually it's not really any worse than anything else we've done. And then this was a problem with a spring in it where we never used the information about what springs do. But if there was a part C that then asked you what the, how much the spring had lengthened because of this motion from its resting length or whatever, then you could go back into that equation that had the spring force in it and put in the equation for it. And I don't know. I would say, like, in a way, what you're trying to do is get to the point where these nasty problems like this really, you sort of recognize what's identical with these problems to the simple looking problems, and the rest of this stuff is just, it's a lot of algebra, but you've been able to do algebra for many years, so. Okay, well, I guess that's class today. See you tomorrow.
Will we get our Friday?
Probably not this week, but Monday probably.
You have to make it while I get my tomorrow.
Okay, I'll try to get it back tomorrow.